You've correctly calculated the required transformer kilovolt amps as 45 kilovolt amps. The primary current is calculated using the formula primary equals kilovolt amps divided by voltage times 1.73. For a 480 volts primary voltage, primary equals 45 kilovolt amps divided by 480 volts times 1.73, which equals 60 amps. The primary panel should be rated for the primary current and voltage. In this case, a 60 amps 480 volts panel is required. The secondary panel should be rated for the secondary current and voltage. You've calculated the secondary current as 125 amps. For a 120/208 volts secondary voltage, the required secondary panel rating is 125 amps at 208 volts. Consider the transformer's efficiency and power factor when sizing it. A dry-type transformer installed indoors typically has an efficiency of 97 to 99% and a power factor of 0.95 to 0.98. The secondary panel should have sufficient capacity for the anticipated load. It is good practice to have an overcurrent protection device on the secondary side of the transformer. The overcurrent protection device should be rated for the secondary current and voltage. Let's delve deeper into these concepts, breaking them down further for comprehensive understanding. Firstly, let's explore the transformer itself. The transformer's primary function is to step down or step up voltage levels. In this instance, you're stepping down the voltage from 480 volts 3-phase to 120/208 volts 3-phase. The kilovolt amps rating of a transformer is a measure of its apparent power capacity. It represents the total power the transformer can deliver, regardless of the power factor. To accurately size a transformer, you need to determine the total load it will supply. This involves summing up all the individual loads connected to the secondary side, taking into account their respective power factors. The formula you used, kilovolt amps equals volts times amps times 1.73 divided by 1000, is correct for 3-phase circuits. It's essential to use the correct voltage and current values in this formula. Secondly, calculating the primary current is crucial for selecting the appropriate overcurrent protection for the primary panel. The primary current is the current flowing through the primary winding of the transformer. It's determined by the transformer's kilovolt amps rating and the primary voltage. The formula you used, primary equals kilovolt amps divided by voltage times 1.73, is accurate. The result of this calculation, 60 amps, indicates the minimum current carrying capacity required for the primary conductors and the corresponding breaker size. Regarding the primary panel, its rating must match or exceed the primary voltage and current. In this case, a 480 volts panel rated for at least 60 amps is necessary. Consider future expansion when selecting the panel size. It's often wise to choose a panel with additional capacity to accommodate potential load growth. Thirdly, the secondary panel's rating must be sufficient to handle the total load on the secondary side. The secondary current is the current flowing through the secondary winding of the transformer. The formula you used, secondary equals kilovolt amps times 1000 divided by voltage times 1.73, is correct for 3-phase circuits. The calculated secondary current of 125 amps determines the minimum current carrying capacity required for the secondary conductors and the corresponding breaker size in the secondary panel. The secondary panel should be rated for 120/208 volts and at least 125 amps. Again, consider future load growth when selecting the panel size. Fourthly, let's discuss the additional considerations you mentioned. Transformer efficiency and power factor play a significant role in determining the overall system performance. Transformer efficiency is the ratio of output power to input power. A typical dry-type transformer has an efficiency of 97 to 99%. This means that a small percentage of the input power is lost as heat within the transformer. The power factor is a measure of how effectively the electrical power is being used. It's the ratio of real power in kilowatts to apparent power in kilovolt amps. A power factor of 1 indicates that all the power is being used effectively, while a power factor less than 1 indicates that some of the power is being wasted. Dry-type transformers typically have a power factor of 0.95 to 0.98. Fifthly, overcurrent protection is crucial for protecting the transformer and the downstream equipment from damage due to overloads or short circuits. An overcurrent protection device, such as a circuit breaker or fuse, should be installed on both the primary and secondary sides of the transformer. The overcurrent protection device should be rated to interrupt the maximum fault current that could occur at that location. The National Electrical Code, or NEC, provides guidelines for selecting the appropriate overcurrent protection for transformers. You can find relevant information in NEC Article 450. Specifically, NEC Table 450.3 provides guidance on the maximum overcurrent protection ratings for transformers. Sixthly, when selecting conductors for both the primary and secondary sides, it's essential to follow the ampacity requirements outlined in the NEC. Ampacity is the current carrying capacity of a conductor. The NEC provides tables that list the ampacity of various conductor sizes based on their insulation type and installation conditions. Refer to NEC Table 310.15 for ampacity ratings of conductors. It's crucial to select conductors with an ampacity equal to or greater than the calculated current. Also, consider voltage drop when selecting conductors. Voltage drop is the decrease in voltage that occurs along the length of a conductor due to its resistance. Excessive voltage drop can cause equipment to malfunction. The NEC recommends limiting voltage drop to a maximum of 3% for branch circuits and 5% for feeders. Seventhly, grounding is another critical aspect of transformer installations. The transformer's secondary winding must be grounded to provide a path for fault current to flow back to the source. This helps to ensure that overcurrent protection devices operate correctly in the event of a ground fault. The NEC provides detailed requirements for grounding transformers in Article 250. Follow these requirements carefully to ensure a safe and reliable installation. Eighthly, consider the location of the transformer. Since you mentioned that it's a dry-type transformer installed indoors, ensure adequate ventilation to prevent overheating. Dry-type transformers generate heat during operation, and insufficient ventilation can lead to premature failure. Follow the manufacturer's recommendations for ventilation requirements. Ninthly, labeling is an important aspect of transformer installations. Clearly label the transformer with its kilovolt amps rating, primary and secondary voltages, and other relevant information. This will help to prevent confusion and ensure that the transformer is operated within its design limits. Tenthly, remember that electrical codes and regulations vary depending on your location. Consult with a licensed electrician or electrical engineer to ensure that your installation complies with all applicable codes and regulations. They can also provide valuable assistance with the design and verification of the system. To reiterate, accurately sizing a transformer involves several key steps, including determining the total load, calculating the primary and secondary currents, selecting the appropriate overcurrent protection, and considering factors such as transformer efficiency, power factor, and voltage drop. By following these steps and consulting with qualified professionals, you can ensure a safe and reliable transformer installation.